Right, yeah, thanks for showing up. So I figured that you might have seen, most of you might have seen type 3 or higher order logic, so I don't have to start with the beginning. So I will rather show you how it's like to work with Agda. So
I thought you were going to ask us to choose something to click on that page and see whether it was populated or not.
You can place your bets, right? So if you want to follow along on my homepage here, you can download the zip file or also some individual files. Right, then the resources, there's the Agda wiki, which sometimes gets some new content. And so Agda is actually at least six incarnation of an implementation of Martin-Löf type theory. I don't know, there was Alpha, Agda, Agda Lite, Agda 2, but there was also some Alpha thing in between. So I don't know. And also it goes beyond the canonical Martin-Löf type theory. We still use the branding. So sorry to Per Martin-Löf about that. Right, so what Agda is actually good for is to write scientific papers. This is witnessed by this page. There's almost 200 entries, and if your paper uses Agda and it's not on the list, please add yourself. This is a wiki. This will help us with the next grant applications, I suppose, so persuade the world that Agda is useful for something. And since Andy suggested it, we can try the game. Here's Agda's documentation. We click onto some random thing. Right, there is some documentation. There's your bets, positivity checking.
This is the
Okay, a bit. Well, it's not that bad. Right. So let's get to the meat. So here's the tutorial. I'm using the standard library, but if you can't use it, there's also this prelude file which just defines some data type, like the empty type as for the false proposition, the empty record, which is the singleton type for the true proposition. Then we have disjoint union for disjunction, and then we have the natural numbers and lists. So that's all which is in this file. Let's go back with escape star. Otherwise, we'll start. Otherwise, I show you quickly how to use the standard library. So you should have in the project root a library file. Doesn't matter what it's named. It should have extension .agda-lib, and then it has to have a name, which doesn't matter either in this case. And then you can write dependencies. So these libraries will be added to your project, and you should also have at least the current directory as include directory here. And then this will pick up from your .agda directory from the libraries file. So this lists a couple of libraries library files which Agda should know about, and then if we can go to the standard library. So this specifies the standard library, and it has the same format as your main file, so it declares a name for the library which you can use in your .agda-lib file, which you can depend on, and then there's a path. Right. So that's a very minimal library management system to at least have something going. So, all right. So I want to give you a tutorial based on a very nice trick of Conor McBride. So he said it took him 15 years to to figure out how to represent binary search trees in type theory in a clever way. So we know type theory, so especially Martin Löf type theory. Oh, that's magic.
Yes.
So the proofs are programs, so especially evidence is data. And if you look at, so we set ourselves now the task of sorting a list through a tree. So from a list, say 5312, we build up some kind of binary tree. For instance, this one. And a binary tree is usually represented with binary nodes and leaves. So we also have these kind of, we have these leaves here, which we usually don't write. So we want to ensure that this tree is ordered, and Conrad's idea was, it's published in a paper, how to keep your neighbors in order. Well, we put the evidence at the leaves. So usually there's no information, but here we basically put the evidence that 1 is less or equal than 2. That is a leaf. Then here we have 2 is less or equal than 3. Here 3 is less or equal than 5. And 5 here is less or equal than kind of top element, and here 1 is bigger than the bottom element. And the nice thing is about this, you never need to use transitivity if you insert new stuff or rearrange your tree. Like you can make rotations if you want a balanced trees. You just kind of the leaves, they don't, I mean, they always stay the same, right? It's always the same underlying list, which has the same structure, right? So in the end, we want to get out a list, and there we have the same. We kind of intersperse the evidence with the data, and so on. So you can see all the rebalancings of the tree will have the same underlying list, so you don't have to change the evidence. You only have to shuffle the stuff around. So this is a very nice idea. So, and I hope to be able to. I hope to be able to demonstrate that we can do this in Agda, and just to be sure, I get to the other parts of the tutorial. I set myself a hard deadline of 15 minutes. If I don't make it in 15 minutes, we just abort this. Let's get to work. So we import stuff from the standard library, which you can also define in your prelude, like the empty type, unit type, the disjoint sum, the list and natural number with the constructors. We don't need more of that. And you can see you can either keep the names from the library, or you can also give it new names. Oops, that goes a bit fast. So, okay, so relations are just binary functions into set. So set is the same as prop in Martin Löf type theory. So we don't have a universe of propositions, so we just take the least universe of types. Yeah, and for historical reasons, this type thing is named set. That goes back to Martin Löf, so that has stuck. But yeah, think of it as type. So this is the lowest level of type, and then relation over type has to be in a. So the type of relations is in type 1.
So there's no prop.
There's no prop. No. Then total relations, and those are total in a decidable way, are those that hold either in one way or the other. So R is total if for all x and y. There is either x related to y or y related to x, and we can actually decide this. And now we want to implement this for the natural number. So let's define, so I load the file with Ctrl+C, Ctrl+L.
Remove your option about unresolved matters.
Why does it not do it? Okay, it doesn't turn these into.
You have to
You-
uncomment your unresolved matters pragma.
Yes.
But it is an interesting effect, I didn't know. Thanks. Okay, so apparently it doesn't allow me to work on this. So, okay, so we want to define a relation on natural numbers, the lesser equal relation, and we do this by cases. So I press Ctrl+C, Ctrl+C, and then I can either split on a variable or on the result. That means, in this case, to introduce the arguments, and then I split on x. So I put x here, Ctrl+C, Ctrl+C. And then in this case, this is always true. So I return the unit type. And here I have to also check on y. So this is always false. I return the empty type. And here I recursively call x lesser equal than y. So this is kind of a computed relation. And then it will either compute to the true proposition or the false proposition. And now I can prove that this is a total relation. I do the same, introduce arguments split on x, so I follow the same pattern of definition. Because now what's happening, so now we have to show here that the relation holds in one way or the other, and Agda has already simplified the goal for us, so it's clear that it holds in the first way, so x lesser equal than y. And now here I would use the left injection and then the trivial evidence. And so there is so I could write in left. Trivial evidence can be, you don't have to write the constructor, so this empty record is thanks to eta expansion, so everything is equal in the empty record. So even if I write a meta variable, which is the underscore here, it will eta expand away to the single inhabitant of the empty record. But also here, to make things nicer, I can define pattern synonyms here. So I have lesser equal, greater equal, and then I use my lesser equal thing. And then in this case, Agda has already decided this should be proof of false or true. So I use the other pattern synonym, and here this has simplified to x lesser equal than y or y lesser equal than x. So I just have to recurse on x and y. Right, and now we use this kind of, well, we now define these binary search trees, but here we kind of abstract over an arbitrary relation over an arbitrary type, but the relation should be total, so we should have a compare function. Now this is an anonymous module which has parameters, so that means the module will always automatically be opened, and these parameters will be abstracted over all the definitions I have there, but it doesn't distinguish whether they are actually used in the definitions or not, because you should statically see that this is kind of the parameter prefix of everything in the module. And also, since we have metas, we can have open metas everywhere. It would not even be clear at every point of time whether these assumptions are used or not, right? I have rows, they could in principle refer to it or not. Okay, so what we first do, we extend the data type A, but by a top and bottom element. So we just have a new data type, which I call bracket A, and then these two new elements and I'm embedding from A into this type. And then we also extend the relation R we have to A bracketed. So here I've already done this, so everything is below top, everything is above bottom, and then for embedded elements we call R, and in all other cases we have false. So what you see here, if you have good eyes, then it's actually better on my screen. So the last two left-hand sides are a bit smoky in the background. So you see, it's hard to see on, as I can see it. So there is a kind of border here around. So this is all in smoke color. That means these are clauses with default. So these are catch-all clauses. So it doesn't matter whether I write an underscore or something here, that doesn't change it. But this means they don't hold definitionally, right? So Agda, if Agda sees bottom less or equal than x, it will not rewrite this to true, because internally everything is translated to case trees, and Agda has while it was constructing the case tree, it already saw in the first clause, oh, I have to match on the second argument. And so at this case, there's three cases for bottom less than something, maybe top, bottom, and embedding. So these equations don't hold definitionally. And to warn you, there's this kind of smoky background. You can also now add an option where you want to be more strict about it. It's called exact split. And then you will actually get an error. Exact splitting is enabled, but the following clauses could not be preserved as definitional equalities in the translation to a case tree. And then you can say, oh, I'm aware of that, so you have to put the pragma catch-all here, so you're aware that this is a... So then this one is fine, and the other is also a catch-all. Right. Okay, so that's a definition by pattern matching. Now let's define these binary search trees. So it's DSTs are indexed by these two bounds, lower and upper bound. So it can only contain elements which are between these two. And the evidence is in the leaf. So to construct an empty BST with these bounds, I need to have an evidence that L is actually below U. Otherwise, if I construct a node, it's just binary T. So I have pivot element, that's the label. And then I have two binary search trees, but now the left can only mention elements between L and this pivot, and the right only between pivot and the upper. Right. And then inserting into a binary search tree will not change its lower or upper bounds, but I can only insert an element P, for which I know it's actually between the lower and the upper bound. And also here we do case split, Control C, Control C. We get the arguments, and now, of course, we have to see if this tree is empty or not. Well, if it's a leaf, then we want to construct a singleton tree. So we have something like node P, and then two leaves. And then here I need some evidence that P is above L. And I can use Ctrl C, Ctrl A auto because that's such a simple goal, so Agda finds it in the hypotheses. And then here I have, say, a left tree and a right tree and a node. And now I have to, of course, check if I get a new element, in which subtree should I put it. So I have to compare P and Q. And so here we use one of the few tactics Agda has. It's the with tactic. And something is wrong. Course error. So what this does is it adds a new argument to your function basically of the type of this with expression, so whatever the type of compare P and Q is. I can cheat here, I can just look it up. So it's the type of Z, it's this P is related to Q or the other way around. And then, so with the effect that you can pattern match on this new argument, right? And if the with expression appears in your goal or hypothesis, then it's also abstracted over. So this is how you can kind of refine. You can case over an expression in your goal. Usually you can only case on variables. So you abstract it and then you can case over. There is a pitfall, even if I now match on Z here. So then you can see I get the new argument is behind the bar here, but this is actually just a nice surface notation for there's actually a new function generated with different arguments, and it's just printed in this way. So so what Agda does not know, but it somehow uses is expected. So unfortunately, it's not true that compare PQ would reduce to in left of X in the branches, right? So even though we split on it, so this should actually be clear. So Agda doesn't keep such constraints around because I don't know about the meta theory of this, so this makes things very difficult. Maybe it's easier to do this in extension type 3. But anyway, so there is a tricks to work around this, that you also get an equality proof that these are actually equal, which you can use explicitly. But it's not somehow magically true. Okay, so now, right, so now we have two cases, so either P is less than Q. Let's make these names nicer. Or Q is less than P. Right, so, and then here I have to insert into the left subtree. So I keep the right subtree, I insert, oh my gosh, I'm out of time. Let me just finish this thing. So I insert P into LT and keep RT. And in the other case, I have to keep LT and insert P into RT. And then here I need to put evidence, for instance, that L is less or equal than P. But so these are all trivial. So the remainder of the proof goes like this. We can build a binary search tree with arbitrary elements from the list by just starting with the empty tree and then inserting one by one. And then we can also define an ordered list which has evidence intersperse the elements and then flatten down to the order list, the tree, and then again in the end the sorting will be a composition of that. So there's a little quirk with the ordered list, so if you do the exercise later yourself, then you find out there is some kind of brainy stuff going on. Okay. But so far so good. Questions about this first part? So this was only pattern matching. There wasn't a lot of dependent pattern matching here, but
So the Mr. Graph is this statement. Can I also have like a match or case expression in that term, which does a similar? I don't have dependent pattern matching.
no, you have. So what this does is it generates a new top-level definition, right? So there's no local case. So you can have there's this extended lambda thing. Where you can do basically a case statement with extended lambda is a pattern matching lambda, and internally also it translates into a new top level definition. But you can use it as a case statement, but this does not abstract in the goal, so this is not the kind of dependent matching. All right. So let's switch back on this. Metas. Okay, let's go to the next part. Co-patterns. Also should put myself a deadline of 15 minutes. So this is about co-induction and records and co-pattern matching syntax we have for that. So here's a new option that tells Agda when it splits on the result, it should write the projection postfix. The default is still prefix because that was the old notation, but as we already saw for the lean, the postfix notations are quite nice. Okay, so if I want to define a co-inductive type like stream, so I would define it as a record and declare it co-inductive, and then I have fields head and tail in this case. So, and tail is recursive, so right, it mentions streams. So opening this record actually opens the module associated with the record. So for every record there's a module of the same name created, only it has color pink, whereas the record type is blue. And this will bring the projections into scope. And now I can define a constructor given an A and a stream. I can make a bigger stream by prepping this in the beginning. And here I do this by result splitting. So all I need to tell Agda is what should that thing be when the head projection is applied. And that should be A. And if I apply the tail projection to this stream, I should get the A as out. So constructors are somehow not native for co-inductive types, even though I can also declare a constructor here if I want it, but it doesn't behave very much differently to this cons, right? So it doesn't behave differently, right? So the thing is, why we construct inductive types by constructors, we analyze co-inductive types by projections. So this is this duality here. And now, for instance, I want to zip two streams together. So I split on the function itself, and now I have to produce something in stream C, and I split on the result. So now I have to tell what should be the head of zipping these streams together, and there, right, it should be F applied to the head of the first stream and the head of the second stream.
I don't know why you like postfix notation. It seems to me for the naive user it's very confusing. I mean, I think people who don't know what you're doing would probably think that you've got zip width applied to F applied to S applied to T applied to something called dot head.
Right.
Right, when you don't really, do you? Because you have parentheses around zip width of FST and then it's dot head of that. And that seems to me less clear than having head of zip width FST.
Yes.
Personal taste, of course, but yeah.
Yes, that's. I mean, what I like about it, it aligns more nicely, and you have the function still in front.
I suppose I could manually put parentheses around to
Yes,
make
so
it clearer.
the thing is, we are used to have the dot bind stronger than
Yeah.
the application, and that's
Going
confusing.
against standard
It's
precedences is a bad
a
idea.
yeah.
So if you
So that looks quite clear. Yeah.
if you want, you can actually put your.
In a way, I think it should do that automatically.
Yes, but then you shouldn't have brackets on the
Yeah.
on the calls there, and that would look nice.
So,
Yeah.
yes, and unfortunately you cannot write this because this is parsed as a name. So the syntax wasn't prepared for this onslaught. So,
But you're not going to switch off being able to have prefixed record projections, are you?
no, I'm not.
Good.
I'm always for backwards compatibility. So. Okay, so right, and this is just a zip with so user refine thing, and then S tail. Okay. And then so the Fibonacci sequence can be written as a pointwise stream addition. So maybe you've seen that before. The head of the Fibonacci sequence is a 0, and the next element, so the head of the tail, is the 1. And to get the rest, I will just pointwise add the Fibonacci sequence to its tail. Oops. So I add it to, and then Agda refuses to take that because it cannot see that this terminates. And the problem is that zip width is for Agda just an arbitrary function with that type signature above. So it doesn't know if it actually will look more deeply, for instance, into the second stream. So if zip width would just take somehow the tail of T, then this would not terminate, because then this would fit tail would depend on fit tail. So we need kind of some kind of continuity property, or this, so sometimes called continuity. So we need to tell Agda that zip width is actually a good guy, which preserves the defineness depth of the stream. So it will only read n elements to produce n elements of the output, right? And so here we can just shout Agda down with screaming terminating, so then it has to accept this. But if we want to do it properly, we have to use size types. So here we add another parameter to streams, which is the defineness depth. So I get a stream. So a stream with defineness depth I has a head, and then if you can give a j which is less than I, then you will also get a stream with defineness depth of j. So that ensures that, for instance, stream 0 would only have a head, and so on. Stream 1 would have one tail, and then we make kind of a limit. So there's also stream infinity, and that will have arbitrary tails. So this kind of violates a bit this strictly less than So this should maybe just rather be read as j is less or equal than I plus 1. Okay, so nothing will change for this cons, only that this, you can see now, increases the definer steps by 1. So if we implement this again, Agda has to check that this actually increases the definer steps, and right, so what is actually required here is we have to produce a stream with definer steps j, where j is less or equal than success of I, so I is a possible value for j, or let's say rather the stream IA is a possible candidate for the solution, so we can give AS. So you have some contravariant subtyping on the size with streams. So you can always kind of reduce the definer steps. That just amounts to throwing away some information, right? So that is subtyping. Okay, so what happens with SIPWIS? So here we're actually saying that if both inputs have definer steps I, then the output will also have that. And now let's here put all the implicit arguments in to see how that works. So you can turn on implicit arguments via the menu or also with the shortcut Ctrl C X H. And that turns them on, and then if I do a split on the result, it will have implicit arguments on, but since it reloads, somehow it switches this off immediately after that. So this is a nice trick to get splitting with all the implicit arguments. And then we can split again. So that was, nothing happens here. This is still the same. And now here I have to produce a stream of definer steps j, and this was inserted automatically, so let's also make that explicit here. Now I have given a size j which is less than I, and I have to produce a stream of that quality, and I have two streams of size I, so by these, so I can take the tail of these by giving the evidence j, so I have some size less than I, so I can actually take the tail. And also I want to make a recursive call with a smaller size to be justified. So kind of, you could see this co-recursive definition of SIPWIS as actually induction on the size. So let's and then here I have to give a stream of size j, so that will be s dot tail applied to j. So that's of the correct. But we don't have to write all these sizes. I mean, Agda will also figure this out, so I can also drop this hidden argument here. Okay, and then we can define Fibonacci as a function mapping a size to a stream of the definer steps. And now the definition will just go through. So here I have it with plus. So then here I need some stream of size j1, where j1 is less than j, which is less than I. So that could, for instance, be fib, and here. So now if you're curious what is going on behind the scenes, we can actually put all the hidden sizes in here. So we have a sequence of 3 sizes, which is decreasing, and then we make recursive call with size k for the first argument, and here we make a recursive call on j, and then take the tail to get down to k. Okay, so this is how you can communicate that. Yeah, so this is a productive co-recursive definition using the sizes if you go through other functions. So I also read that Isabel has something where you can define, for instance, zipwidth as a friendly function, and then you can use it in that way. So they have a friendly would be which is actually preserving the depth in this way. So here it's kind of an extension of the core. I think in Isabel there's they reduces to the basic HOL with by defining. I think it works like you define new co-inductive types and then you interpret them back. So you would. Okay. So I'm out of time for this part as well. What could be more? So I also did an example where I have representation of decidable formal languages as, so usually formal language is a set of words and they can be organized in an infinite trie, so which branches over each letter at each node. And then this will be a co-inductive type, and then you can define some languages, for instance, you can basically define all the regular constructions on languages using these size tries. So, but okay, I'm out of time, so let's quickly review some other features. No, somehow here it worked. Okay, so let's have a brief look at rewriting. My phone is actually googling for let's have a brief look at. Interesting. Magic. So here's a hack which is 3 years old. Rewrite rules in Agda. So you can actually define, you can add arbitrary rewrites, like rewrite this term to that term, to Agda, to this definition of equality. And so you can actually screw yourself up badly, you can rewrite true to false. And so there's no check about it, but it's sometimes useful as a kind of cheat to get to your goal more quickly. For instance, if I want to prove that appending the empty vector to a vector gives the same vector, I can't even write that down. Oh, now we are back in the same thing. So I can't even write it down because the type of axis is n, vec n, but the type of axis plus empty vector is vec n plus 0, and that doesn't reduce to n. So I want some stronger definitional equality on natural number. For instance, I want to add this fact that n plus 1, n plus 0 is propositionally equal to n. I want to add this as a rewrite rule too. So, so what I have to do is I have to first tell Agda what is my rewrite relation, and that should be here propositional equality. So that only tells Agda how to parse this type as a rewrite rule. So now if I say use the type of +0 as a rewrite rule, you rewrite this, then Agda can kind of pick up what is the left hand side, what is the right hand side. So, and then this will be a rewrite rule for all possible n. And now after this, I can now give access because the type of this has been rewritten to vec an. So they have the same type, and then it's easy to do. There's another, so this is another feature. So here I have to prove this statement, and which simplifies to x cons x plus nil, right? So I can either use congruence with x cons and then apply the induction hypothesis, or I can rewrite x's plus empty to x's, and that's actually not the built-in rewrite, but there's another tactic which is implemented in terms of width, which will try to apply a propositional equality to a goal. And so if I apply this equality, then my goal will just be this one, which I can easily prove by reflexivity. Okay, so there are kind of, I'm sorry also for the confusion, because there's now two things which are called rewrites. But this is really, this is conservative. This just uses, generates auxiliary function just like the width. And it does some match on an equality proof. Whereas this built-in rewrite thing is really extending definition equality.
You can't, as it were, unfortunately, declare your rewrite in the middle of a proof, right?
Yeah.
After having proved the first line is REFL, you could declare it a rewrite and make the second line rather easier.
That's something you should think about. I mean, I also thought about the context of lean. If you, while you're proving a lemma, you can already use it as simplification and you get the same benefits. Okay.
Is there any way of marking your rewrite, your definitional rewrite as sound, in terms of like, is a way of marking it to Agda that it is actually true and therefore it'll pass the safe checks?
Yeah, but it's not necessary because there are no checks.
Easy. Okay.
But you should be on the safe side if you prove the propositional equality and then add it as a rewrite. So the only thing that can happen is that you make Agda non-terminating.
Yeah, so you
by adding commutativity.
may not be able to prove true equals false, but you could spend a lot of time not realizing.
Right.
So you can give an arbitrary relation as built-in rewrite.
Yeah, you can even just postulate something which has the form A arrow A to set, so which is form of a relation, and then you can. It doesn't have to be propositional equality. So then you can postulate some true is related to false, and then add this as a rewrite. So there's no check, so you have to know what you're doing. There might, maybe if the people on the Dukti make progress, or we can steal some of their checks for Agda. Okay. Now I have like 3 minutes for the latest crunch here. Cubicle. This has been implemented by Andrea Vezzosi, our PhD student, and you can get it if you install the current master version of Agda. It's 2.6.0. It's not released yet and use the option cubicle. And then you have this version of cubicle Agda. So I must say I don't understand this very well myself. So some of you might understand this much better, but actually what you have here, you can postulate an equality relation and a kind of this interval-dependent equality relation, and then bind it to things that cubicle Agda will understand. So cubicle Agda has these paths and path P, which you can give your own names using that scheme here. And then it has some built-in primitive partial and print comp, which I can't explain to you now, but I have kind of defined a simpler version which of print comp, which is sufficient for many cases. So that says if you have an interval-dependent set, it could also be a set in a higher level, which could also be dependent on the interval, but then you can, and you have something in A at the first endpoint, then you can go to the second endpoint. And this is implemented some way. But so I could call it drive. You can drive along this path, right? And I'll show you in a minute. So first, reflexivity. How do you prove reflexivity here? So reflexivity. Now, if you split on result, you also you get an element I of the interval, and you should think of the equality type now as a function from the interval to A in this case, where at the first, at I0 it's x, and at I1 is also x. So we now have to produce, given an arbitrary I, we have to produce an element of A such that for I equals 0, this will be x, and for I equals 1 also be x. So we can just give x here. So this is then the constant path. And then substitution. So given a path from x to y, we want to go from px to py. So we can do this with the drive thing. So drive expects a type that is dependent on interval value, right? And now we should we have to give a type, and we want it at I0 to be this px, and at I1 we want it to be py. So what we do is just we take p, and now to get to x at I0 we can use our path p, right? Applied to I, so this is already the right thing. So this is substitution, right? So we can drive from px to py by using this path from x to y. Just going concatenating, basically composing it with p. Okay, and then there is a symmetry, which is just reversing the direction of the path, and transitivity. There's two ways to implement transitivity. So we can go from x to y. Well, the easiest is we take p and then drive from y to z using q, and then we have x equals c. So let me see if I can do this. So we want to 5 using Q, and here we have to give. So here Agda doesn't tell you a lot anymore because it just says I want to set like a type, right? But there is stuff in the constraints, so with Ctrl C, Ctrl equals, you can see some constraints. Oops, that's a lot. Let's uncomment the rest. So it actually says yeah, I think this is not really well engineered yet. There's constraints which so let's see. So what I wanted to yes, I want to keep x fixed and then drive what was this? EI? No.
Q.
Yes. So I think I did this one.
But then you need to provide this.
Yeah, I think I'm lost out.
And you also need to use P as the arbiter, X plus parameter for graph.
Well, I think I did this one. Not to go from right to Z.
I think the final argument of drive probably is
Yeah.
As I said, you understand this better than me.
Because you're standing a bit further away from it.
Okay. So now this makes I mean, combining this with co-induction makes things.
Semanticist nightmare.
No, this makes things very neat because now we can use this passes also for using it for bisimulation of streams, right? So a very simple example: I have my streams, and I have two different repeat functions. One will put out an element A, and each time the other will put out two A's, right? And these are not definitionally equal, and so we basically have to prove. We want to prove that they are equal by co-induction, so they are bisimilar. So let's just dive into this. So prove that repeat, same as repeat 2. And now I have to give a stream. So because equality is the function from interval to streams. So now I just do my splits here. Okay, here I have to produce an A here as well, and here I can just recurse. No, I have to produce a stream. Okay, perfect. So then the proof is kind of what we skip here is the definition of the bisimilarity relation, which would be a co-inductive type, and then we prove the reflexive, symmetric, transitive, and especially the substitutivity that has to be done for each function if we use the co-inductive bisimilarity. And here we have substitutivity just because we get it from two. So you can, so this is actually works very nicely. So same if you have the map function over streams and you have the iteration, which produces the stream of A, FA, FFA, triple F of A. We could, for instance, prove that if I map F after I've iterated F, so I map F over the iteration of f, it's the same if I apply f to the start value and then do this iteration, right? So this is so let's see how to prove this. So we have to produce a string. So let's do this. And here we have to produce an A. That should be f of x in both cases, and here we want to recurse. Right, so that's yeah, that's kind of a technology preview which will hopefully come soon. Yes, all my students will implement the rest of this. Okay, that's all. Thanks for your attention.
So as Andy said, so the last example is probably a nightmare semantically. So no? Did you check that we actually have co-induction and
It's actually very simple. It's a string, so you define a string of a semantically, if A has a composition structure.
okay.
How far off release is 260?
Yeah, I don't know.
I suppose it's not a fixed amount of time, really, is it?
Well, probably will release in fall. I mean, the plan is to release something for the Agda meeting, and it's probably the case we rather release the cubicle in that raw form for people to play around with than to wait long for the polishing. But, so I hope this will be some in September.
So how difficult is it to add other features to Agda? I'm thinking about guarded recursion, but it's in general.
Yeah.
It's a very easy procedure. You get a clever young person and you send them to Gothenburg and wait 6 months.
I think Andrea is extremely efficient in doing that. So for me to add co-patterns, there was a process going on for 4 years. I mean, there's still some features which don't work with co-patterns, but depends on how much time you have at the same stream. One stream. The main challenge is that everything has to work with meta variables, and meta variables can be in any expression. So I think this is the main challenge of Agda to implement, because you always have to be able to postpone your analysis until this meta variable has been instantiated. So you have to think more in terms of constraint programming, that you generate constraints and then you come back to them once you know more.
Yeah, but I think this is very nice because it seems very, from what I understand, it seems very difficult to add cubicle to conc. So this will be one motivation for people to actually use that.
I suppose the cubicle addition is not documented. I mean, again,
Yeah, there's some documentation.
Is it?
Yeah.
I think you have to go to the, I don't know how to switch to version 6. And then there should be some.
Oh, I see. Okay.
No documentation.
You mean there's something in his GitHub?
I'll send you a link.
Yeah. Well, you don't need much, but you do kind of need to know what the primitives are
Yeah.
that have been added.
Yeah.
What they're called.
So when will you add tactics like that?
There is already a tactic language. Well, there's a reflection language where you can do things a bit in a similar way than Jeremy showed. I didn't show it because I'm not so familiar with it. But
Is that Ulf doing that mainly?
yeah. But there's the same, you can get a call in a kind of data type representation, and then you can manipulate, you can call the unifier, you can call the checker, type inference, all that stuff. Right? It's only not as nice as Steam because you can't use Agda syntax to manipulate this data type of Agda expressions. You have to use the constructors of this data type, right? I think what you have is back quotation.
Yeah.
Thing is not there. But people have implemented auto takt